Today, we are looking at 10 diagnostic tools that lived in every serious American mechanic's garage between 1958 and 1968. None of them needed a battery. None of them needed a plug. None of them needed a screen, a software update, or a scan code. They needed a man who knew how to read them. Number 1 is the tool that told a mechanic everything wrong with an engine before a single bolt was touched. Let us get into it. Number 10. The feeler gauge. A fan of thin steel blades riveted at one end, each one ground to a precise thickness measured in thousandths of an inch. The blades ranged from 4 thousandths to 40 thousandths, stepping up in increments finer than a human hair. The mechanic selected the right blade, slid it into the gap being measured, and felt whether it moved freely, dragged slightly, or would not pass at all. That feeling was the measurement. No display, no readout, just resistance transmitted through steel into a fingertip. The feeler gauge set the spark plug gap on every car made before electronic ignition. It set the valve clearance on overhead valve engines. It checked the breaker point gap inside the distributor, which controlled how long the ignition coil charged before firing. Every one of those measurements affected how the engine ran. Too wide a gap and the spark was weak. Too narrow and the spark came too early. The feeler gauge was the difference between an engine that ran clean and one that fouled its plugs every 3,000 miles. The modern replacement is a wire gauge for spark plugs and electronic valve adjustment tools that require the engine to be warm, running, and connected to a laptop. The feeler gauge required none of that. It required a cold engine, a steady hand, and the ability to tell the difference between a blade that slid freely and one that dragged. That distinction, felt in the fingers rather than read on a screen, told the mechanic exactly what he needed to know. Number 9. The mechanic's stethoscope. A steel probe attached to a rubber hose attached to a pair of earpieces. The probe was pressed against the engine block, the valve cover, the water pump housing, the alternator bracket, the steering gear. The mechanic listened. The engine spoke through the steel and the rubber and into the ears of the man who knew what the sounds meant. A worn main bearing produced a deep, rhythmic knock that came up through the block at low RPM and softened as the engine warmed. A failing valve lifter ticked at the top of the engine in a pattern that matched the camshaft speed. A bad water pump bearing whined in a pitch that changed when the engine was revved. A loose timing chain rattled on deceleration with a sound that had no equivalent in any other failure mode. None of these sounds required electricity to detect. They required a probe, a hose, and ears that had listened to enough engines to know what healthy sounded like. The modern equivalent is a chassis-mounted microphone connected to a laptop running acoustic analysis software. It costs $4,000, takes 20 minutes to set up, and still cannot tell you what an experienced mechanic's ears knew in 30 seconds through a $5 probe. Number 8. The vacuum gauge. A round dial in a rubber housing connected to the engine's intake manifold by a short rubber hose. The needle moved to a number measured in inches of mercury. That number told a story, and the story covered almost every major mechanical condition an engine could develop. A healthy engine at idle held steady between 17 and 21 inches. A leaking intake manifold gasket caused the needle to flutter in a narrow band. Worn piston rings pulled the reading down to 12 or 13 and held it there. Late ignition timing pushed the reading low but steady. A burnt exhaust valve caused the needle to drop sharply at regular intervals, matching the firing order of that cylinder. Sticky valves caused the needle to flutter widely at idle and stabilize at higher RPM. One gauge, one hose, one connection to the intake manifold. A mechanic who understood vacuum could stand at the front of the car, watch the needle for 30 seconds at idle, and name 4 separate mechanical problems without opening the hood again. The OBD scanner that replaced it reads error codes thrown by sensors. The vacuum gauge read the engine itself. Those are not the same thing. Number 7. The compression tester. A rubber-tipped probe connected to a pressure gauge by a short reinforced hose with a Schrader valve in the line to hold the reading after each test. The mechanic pulled the spark plugs, threaded the probe into each hole in turn, cranked the engine for 4 revolutions, and read the pressure. Normal compression on a gasoline engine of the era ran between 120 and 160 pounds per square inch. Every cylinder told part of the story. Together, the cylinders told all of it. Two adjacent cylinders reading low meant a blown head gasket between them. One cylinder reading 0 meant a burnt valve or a holed piston. All cylinders reading uniformly low meant a worn engine that needed rings. One cylinder reading high meant excessive carbon buildup on that piston crown. Squirting a small amount of oil into a low cylinder and retesting told the mechanic whether the problem was rings or valves. If the reading climbed with oil, the rings were worn. If it stayed low, the valve was the problem. The entire test took 15 minutes. It required no electricity, no computer connection, and no access to a dealer's diagnostic network. It required a gauge, a hose, and the understanding that an engine's health was written in its cylinder pressures for anyone willing to read them. Number 6. The oil pressure test gauge. Not the gauge on the dashboard. That gauge was connected to a sender unit that gave a relative reading, not an absolute one. The mechanic's oil pressure test gauge screwed directly into the engine block where the sender had been. It read actual oil pressure in pounds per square inch against a calibrated board-on tube inside the dial. No electricity involved anywhere in the measurement. A cold engine at startup should produce oil pressure within 3 seconds of cranking. A worn oil pump showed low pressure at idle that climbed to acceptable numbers at higher RPM. Worn main bearings allowed oil to bleed past the clearances and dropped pressure at idle. A blocked oil passage caused pressure that was fine at the pump but could not reach the bearings that needed it. The dashboard oil light told a man his oil pressure had already dropped to a dangerous level. The test gauge told him what the pressure actually was before anything was in danger. That is the difference between a warning and a diagnosis. The light tells you the house is on fire. The gauge tells you which room and how hot. Number 5. The tire pressure gauge. A steel barrel the length of a finger with a rubber tip on one end and a calibrated stick that extended from the other. The mechanic pressed the tip onto the valve stem, the air pushed the stick out, and the pressure was read from the markings on the stick. No battery, no digital display, no zeroing procedure, no low battery warning appearing at the worst possible moment. The pencil gauge read tire pressure in under 2 seconds and did it accurately to within 1 pound per square inch. It fit in a shirt pocket. It weighed less than a pocket knife. It cost less than $1 at any filling station in the country, and it never needed replacing because the only part that could fail was the rubber tip, which cost nothing to swap. Tire pressure in the 1960s was not just a safety concern. It was a diagnostic one. A tire wearing on the outside edges ran underinflated. A tire wearing down the center ran overinflated. A tire wearing on one edge only indicated an alignment or suspension problem that was pulling the car to one side. The mechanic who checked pressures every week caught problems before they became failures. The modern digital gauge requires a battery and gives the same reading the pencil gave 60 years ago. The pencil is still more reliable because it has nothing to go dead. Number 4. The cooling system pressure tester. A hand pump connected to a rubber cap that fit over the radiator neck. The mechanic pumped the handle until the gauge on the pump read the system's rated pressure, then watched the needle. If it held, the system was sealed. If it dropped, there was a leak, and the leak was visible because the pressurized coolant pushed itself out through the failure point while the cap was on and the engine was cold. No electricity involved. No running the engine hot and burning hands on a radiator cap. The pump pressurized the cold system to the exact pressure the thermostat and radiator cap controlled during normal operation, which meant the test replicated the conditions that caused leaks without any of the danger of a hot system under pressure. A mechanic who used this tool caught a weeping hose clamp, a pinhole in a radiator tank, a cracked coolant reservoir, and a seeping heater core before any of them stranded a car on the side of the road. He caught them in his garage on a Saturday morning for the cost of a hand pump and a set of radiator cap adapters. The modern version of this tool is identical to the one from 1964 because nothing about cooling system physics has changed in 60 years. Number 3. The ball joint and tie rod checking bar. A steel pry bar, usually 18 inches long, flat on one end and curved on the other. The mechanic placed a floor jack under the lower control arm to unload the suspension, put the flat end of the bar under the tire, and pried upward. He watched the ball joint. Any movement visible to the eye was too much. Then he grabbed the top and bottom of the tire and pushed and pulled while watching the tie rod ends. Any play there meant the steering geometry was shifting with every bump in the road, and the car was wearing its tires unevenly while steering imprecisely and endangering anyone inside it. The test took 2 minutes per corner. It required a bar, a floor jack, and eyes. No measurement equipment, no electronic play detector, no dealer diagnostic session. The standard was binary. Movement meant replace it. No movement meant it was good. A mechanic who ran this check every time a car came in for an oil change caught worn suspension before it became an accident. The mechanic who skipped it because the customer had not complained found out later in a different way. Number 2. The brake drum micrometer. A C-shaped frame with a calibrated thimble and a ratcheting spindle that measured the inside diameter of a brake drum in thousandths of an inch. The mechanic opened the drum, seated the micrometer across the swept surface, and turned the thimble until it contacted the metal. The reading told him exactly how much material remained and whether the drum was within specification for safe use. Every brake drum had a maximum diameter stamped on its face. That number was not a guideline. It was the point beyond which the drum wall was too thin to contain the heat generated during a hard stop without cracking or warping. A drum at maximum allowed diameter was a drum that would fail under the first extended downhill run on a loaded vehicle. The micrometer was the only tool that gave that number accurately. Visual inspection gave nothing. Running a finger across the scored surface told a man there were grooves but not how deep. The micrometer told him the exact inside diameter, whether it was at specification or beyond it, and whether machining it would take it past the limit. That number determined whether the car was safe to drive or not. It was not an estimate. It was not a judgment call. It was a measurement, accurate to a thousandth of an inch, made without a single electrical component. Number 1. The Vacuum Advanced Diagnostic Cap. A machined aluminum cap that replaced the distributor cap on any Points ignition engine. A vacuum line connected the cap to a hand-operated vacuum pump with a gauge built into the handle. The mechanic applied vacuum to the advanced mechanism inside the distributor, held it at a set level, and watched whether the vacuum held or bled down. If the vacuum held, the advanced diaphragm was intact and the distributor would advance timing correctly under load and cruise conditions. If the vacuum bled down within 30 seconds, the diaphragm had a pinhole or a cracked rubber port and the engine was running on fixed timing at every speed and load. An engine without functioning vacuum advance burned more fuel, ran hotter at highway speed, and wore its valves faster because the combustion event was not timed correctly to the engine's actual operating conditions. The test took 45 seconds. The hand pump cost $4, and the information it provided explained symptoms that 3 separate mechanics had diagnosed incorrectly as carburetor problems before someone thought to test the advanced diaphragm first. 10 tools. None of them needed a wire. None needed a code. None needed a software subscription, a dealer login, or a module replacement. They needed a man who understood that an engine communicated constantly to anyone who knew the language. Pressure, vacuum, sound, play, measurement. Those were the words. The tools were the ears. We replaced them with scanners that read error codes. The scanners are faster. They are also only as informative as the sensors that feed them. A sensor that has not failed yet reports nothing wrong while the engine tells a different story to anyone listening with a probe and a gauge. The old tools heard the engine. The new tools wait for the engine to admit defeat.